Thank you to all the organizers for the invitation. C'est mon plaisir de revenir ici à Lumini. So the talk I'm going to give is more or less colloquium-style presentation. I want to, especially since there are many graduate students or junior researchers here, I want to somehow trace my trajectory in research in complex geometry. I started with several complex variables in Kähler geometry, and then I sort of move on in different directions. I think it's a good idea that you focus on something that you want to, with some historical importance, and you want to do mathematics as sort of a development of building on works of giants in the history of mathematics. And one of the major themes I had was the uniformization theorem. So for the uniformization theorem, I work in different directions in positive curvature, asymptotically, positive curvature, and then also non-negative curvature, and then negative curvature. So today I'm more focused on studying omega mod gamma. So omega being a bounded symmetric domain, so this belongs to the hyperbolic case of the uniformization theorem. So okay, so I start with something that everybody knows, just to set the background. So this is the Berman kernel. The Berman kernel is defined by the space of square integrable holomorphic functions. The better way to describe it is that it's defined by square integrable holomorphic n forms, because the norm is then invariant, independent of the choice of coordinates. So this Berman kernel, and this textbook proof that this gives you the Berman kernel independent of the choice of an orthonormal basis. The reason being that it satisfies the reproducing property, and that uniquely determines the Berman kernel. And then you prove that when you take the log of the Berman kernel restricted to the diagonal, you get what is the Berman metric. Now, of course, the Berman kernel is not invariant. The Berman kernel form is invariant. So you have to multiply by the dz1 wedge dzn absolute value square. But then when you take the bar log, this becomes invariant. Again, it's best to look at this as defined by the Berman kernel form instead of the Berman kernel function. And its positivity on a bounded domain is easy to check because you can choose a good basis to do it. Now, then my focus would be on bounded symmetric domains. The first examples would, of course, be the case of the ball being defined by norm of z being less than 1. And these are the classical domains. The classical domains type 1 to type 4. So the ball is a special case of type 1. And one has a Mordell embedding theorem. You have of course, you have the compact dual. This is duality in Riemannian geometry. The bounded symmetric domain is equipped with the Berman metric. And if it's irreducible, then this is a Kähler-Einstein metric. All right. So then you have, these are symmetric, Hermitian symmetric manifolds. They have their dual. And the Mordell embedding theorem tells you that one is embedded sort of canonically in the other as an open set. So for instance, the ball is embedded in projective space, type 1 domain into Grassmannians. Type 3 domains, which are equivalent to Ziegel upper half-planes, are embedded in Lagrangian Grassmannian. So there are two exceptional cases, the 16-dimensional and 27-dimensional ones pertaining to E6 and E7. In a way, it's good that we have exceptional domains. Then you have to develop the theory independent of special choices of bases. Well, of course, you can also use root vectors and so on. So one thing I want to say is that the Berman kernel, when you consider it as a function of z and w bar instead of w, is a rational function in z and w bar. This is also the case with the exceptional domains, and you can prove it theoretically. Now, so the title of the talk is starting with Gauss-Bonnet formula. So Gauss-Bonnet formula is something that everybody knows, whatever your subject of study. And then the first theorem I stated something a long time ago. I did in 1987, where I consider the quotients of bound symmetric domain. First, the co-compact cases of irreducible and of rank at least equal to 2. Then the background is, of course, that there was already in the 70s Margulis superrigidity theorem. Well, it has consequences on maps or representations of fundamental groups and so on. But by making use of this uniqueness theorem, one can get such rigidity theorems for Archimedean, well, in the case of holomorphic maps. One can start with harmonic maps and prove them that they are holomorphic or near being holomorphic. They are pluriharmonic maps using the method of Mok-To, the DD bar Bochner-Kodaira formula, and then you prove that this is a total geodesy. So the statement here is that it's actually total geodesic and isometric up to a constant. So in the case of finite volume, former student of mine, Wing Kang To at NUS, where he proved the generalization without any bound, a priori bounds on the metric. So there's a uniqueness of the Hermitian metric of semi-negative curvature. You may restrict to the Kähler case, and but in general it holds true for Hermitian case, but you should state the curvature slightly differently. Yeah. So then here is a consequence. Then, okay. Yeah, if you have the strong rigidity result from Mok-Seo, the homotopy type determines the complex structure up to conjugation, and then in the case of higher rank, then the metric is also determined, right? Because of the uniqueness theorem. Okay, so this was the summary of the proof. You represent the map. I'm in the compact case. You represent the map by a harmonic map. You prove that it's pluriharmonic, and then well, in the case of equal dimension, actually, it could be proven that it's either holomorphic, anti-holomorphic by the work of Mok-Seo, and then, but even without that condition, it's possible to prove that you have total geodesy. Yeah. So I want to say something about the proof. The proof comes from a Gauss-Bonnet formula. In our context, it is actually a Chern integral. But let me just very briefly explain in terms of a very simple example. If you have a map, let's say you have, maybe it's better that I write on this board. So if you take x into y, a holomorphic map, and f is non-constant, and you take x to be C mod L, so this genus 1 here, and this has a genus bigger than or equal to 2. Does there exist such a map? Of course, this is a very simple problem. If you have, well, you take a holomorphic one form and you pull back, you get a contradiction, right? So the answer is that does not exist. But it is possible to prove this metrically. Because why metrically? Because metrics are more easier to manipulate, right? So you can take the metric here, the Poincare metric, and you pull back, and you plus the flat metric, the Euclidean metric, and call this metric H. Now this is certainly a metric. It is already there's a metric, and then you see that the Gauss curvature of this is actually less than or equal to 0. This is by the Gauss equation. So this is flat, and this is negative curvature, and some must have non-negative curvature even with the genuses. And then you have the Gauss-Bonnet formula that integral over x Gauss of the flat metric is equal to integral x Gauss of H. This is 0, identical 0, and this is less than equal to 0. And from there, you get that actually the map is, cannot exist. Right? So just vanishing of the curvature at every point implies the map is constant. Okay. So this is a little, well, more amenable to manipulation. So because these are just functions instead of holomorphic functions, positive functions, and so on. So then how does one prove, for instance, in the case of zero-modular variety, of course it has finite volume, then you look at some set inside the tangent bundle or the projectivized tangent bundle where you have flats. You have zeros of bisectional curvature. So here it's making use of the fact that this is flat. So of course in the case of of omega mod gamma of rank irreducible and of rank at least 2, you don't have flats, but you have embedded flats, right? You have embedded flats. So this from Riemannian geometry, you have the maximal tori and so on. And the tori, when you complexify them, what you get are polydiscs. And these polydiscs give you the carriers of the zeros of bisectional curvature. So I use, in a very important way, the bisectional curvature. And when you use the bisectional curvature, here is the important relation that one should make use of. Is there an eraser? Oh, okay. One should make use of. Yeah, I can do here. When you have a vector bundle over a manifold, complex manifold, you can associate to it PV. Well, so you have, from here you have this projectivization over M. And then there's a line bundle over PV. And this curvature, so if you have a metric VH here, so then it has a certain, this is called the tautological line bundle. The important thing is that if VH has negative curvature in the sense of Griffiths, this bisectional curvature in the case of Kähler metrics on the tangent bundle, if this is less than or equal to 0, implies that the Gauss curvature of the associated is less than or equal to 0. So as a whole, this is essentially the same as V. You just blow up the 0 section, right? So then this Gauss formula is about metrics on the holomorphic line bundle, Hermitian metrics, and this is where the proof comes. Is it possible to turn? All right, yeah. So, yeah. So I introduced a certain concept. This concept later was termed the VMRT when I study positive curvature, but today I'm talking about negative curvature situation. These are just the orbits of the highest weight vectors. So for instance, if you are in case of classical domains of matrix type, then you're talking about rank 1 vectors or rank 2 vectors in case of skew symmetric matrices. And this has a certain orbit. This is G mod K. You take the K orbit of a highest weight vector. This is holomorphic. And as the base point change, actually this is invariant under the group, and you have something on the complex group even. So it's something which defines a holomorphic fiber bundle. So I'm looking at a line bundle over the projectivization of tangent bundle. You restrict to this highest weight orbit fiber bundle, which is the same as the restriction of the VMRT to omega modulo gamma. Yeah. Now on that, and you take this line bundle with the Hermitian metric, induced Hermitian metric, and this has curvature less than or equal to 0, and there are, if you take a point, I think you can still see it in the dim light. Yeah. If you take a point alpha belonging to Cx, It's all right. I think people can see it. Mod gamma. Then there exists zeta not equal to 0 such that the curvature, so this is the important thing, that there exists some zeta for which the bisection curvature is equal to 0, and therefore LH has some 0 eigenvalue. What remains to check is that can I have some meaningful formula? You restrict this semi-negative form. You can, of course, the semi-negative, I can just look at minus C1 of tautological line bundle. So this is the, maybe G is the initial metric, and let me take a Hermitian metric and induce. So this is going to be bigger than equal to 0. So I put the minus sign here just to make it easier to say. So then you have this guy, and then I want to integrate this over some subset instead of all the tangent bundle. The only thing to check, or whether this gives me anything meaningful, the only thing to check is that the 0 eigenvectors are tangent to the subset. And I check this by using Harshchandra realization. But I want to say that there's actually a better geometric way to understand this is from the Polydisk theorem. The Polydisk theorem says that you have this polydisk inside. And obviously, the 0 eigens vectors, spaces, are tangent to this product, because it's a product, it's a Cartesian product. And then the set where I do the integration of C, omega mod gamma. This I sometimes write. This is actually the union, so to speak, union of the polydisks. So polydisks. If I just do it on omega, you can make it into union of polydisks. And from there, one can prove actually the tangency without using coordinates. So this is a more conceptual proof. And it turns out that this interpretation is also very important. It's not just union of polydisks. You can put it differently. You put it as delta across omega prime, which has rank R minus 1. So this omega is rank R. Then it's this product structure which underlies the structure of zeros of holomorphic bisectional curvature on omega. So this function theoretical interpretation then became important when we study proper maps. Okay, so it's important, of course, one tries to prove new theorems, but it's also important to know why something is correct from different angles. A different angle gives you a different possibility of development. That's what I want to tell the newcomers to mathematics, that a perspective I find very fruitful in doing mathematics. Okay, so I'm just putting down the proof in terms of what I already explained over there. And here, the first term form of tautological line bundle. So the zeros of curvature has something to do with the zeros of this induced metric. I use S here in the notation. And then you're allowed to take sums, because taking sum preserves the property of semi-negativity. It does not preserve the property of semi-positivity, only semi-negativity. So it's important to work with negativity. And again, if you look at this Chern integral, what you have is actually G is the canonical Kähler-Einstein metric. H is a given metric. You may assume this to be Kähler or even just Hermitian. You put in this formula, and then you get, on this side, this is equal to 0 by computation, because of the 0 eigenspaces are tangent to the subspace. And this is just cohomological. They represent the same cohomology class, and therefore you have this formula. So H can be taken to be the sum of two metrics, again by the Gauss equation. And this is how it was proven. Yeah, so the highest weight orbit can be described as follows. If you use the omega hat to be the dual manifold, and omega sitting in omega hat as being the Borel embedding, So you can define this from the Grothendieck decomposition. And then the Q, when you have this decomposition, O to the power Q, this is actually coming from the tangent vectors of this omega prime here. Yeah, so I have this factor of rank R minus 1. So this gives you the flat directions associated to the minimal rational tangent, or the tangent to the minimal rational curve, projective lines, and so on. Yeah. So this is the technical language that one uses with the Harris-Chandra realization. The way to check is that translation preserves the flats, and so it's easy to check this way. But as I explained, the underlying geometric reason is because of the embedding of the polydisks. Okay, then now I move on to something seemingly unrelated, to go to elliptic curves. So I was, of course, first interested in omega mod gamma, so where I proved the rigidity. But then there are some omega mod gamma which are omega mod gamma which are more important. Namely, you can look at those which parameterizes abelian variety. So the first example would be to those who parameterize elliptic curves. Okay, so when you have an elliptic curve is C mod L, and this is very classical, two lattices would define equivalent elliptic curves if and only if there's a relation given by SL to Z. So this is a J function. A J function serves as something like the exponential function, except that when you mod out by SL to Z or PSL to Z, you have fixed points. If you want to remove them, then you introduce a level N structure. So taking those elements which are congruent, for instance, congruent to the identity matrix mod N. So N sufficiently large, you can get things without fixed points. But the J function is very important. The J function is a quotient of two modular forms, and they are defined by the lattices. Okay. So because there are fixed points, this is not a contradiction. This is actually isomorphic to C, because when you mod out, you have fixed points. The curvature has singularities. Yeah. Okay, so the first balanced symmetric domain, or something equivalent to a balanced symmetric domain, the Ziegel upper plane. Because from elliptic curves, you go to abelian varieties. And you look at those which are so-called principally polarized. Anything that's polarized is somehow isogenous to one which is principally polarized. Depends on the first Chern form, right? And the parameter space is then given by the Riemann bilinear relations. This says that you can assume if it's projective, that the lattice be spanned by the usual basis factors together with symmetric matrix, a complex symmetric matrix, whose imaginary part is positive. These are the Riemann bilinear relation. This comes, if you think about representing them by forms, it comes from simply the symplectic structure by taking wedge of two forms and integrating, like in the Jacobian. Right? Okay, so the symplectic group acts on Hg, and the arithmetic subgroup acts on Hg as a discrete subgroup. Okay. Okay. So then this gives you the analog of SL2Z, and this parameterizes the space of principally polarized abelian varieties. So it's this quotient which is one of the most important moduli spaces. Even the moduli space of Riemann surfaces maps into it through the Torelli map. So this is a very important space. And this is biholomorphically equivalent to type 3 balanced symmetric domain. So defined by the inequality together with the property that the matrix be skew symmetric, be symmetric. Yeah. So the matrix inequality is the same as for type 1, but you assume that the matrix is symmetric. So you have the Ziegel modular variety. So why? In general, if you take an arithmetic subgroup, the quotient is called a Shimura variety. So this explains why I was interested on the Shimura varieties. Now I want to say something more in complex analysis of several complex variables, which is something very popular already in the 70s and 80s. Up to today, we see a lot of work on using current. So the theory of positive closed currents by Pierre Clelon and much developed by Skoda. So I am going to study moduli spaces of abelian varieties, satisfying additional conditions. So these are techniques that are used to study currents. I will explain why they are useful. So this is the monotonicity of the volume, or weighted volume, weighted by the volumes of the flat subspace passing through the origin. This monotonicity allows one to define density number, the Lelong number, so this is familiar to everybody here. And then the Yam-Tong-Seo proof an essential theorem in which you can, from a current, recover a subset with positive density bigger than or equal to C. So this is the analyticity of this set. Of course, an important ingredient is d bar, L2 estimates of d bar of Hermann. Okay, and Skoda proved a very important theorem about extension of closed positive PP currents. You can extend a current across a subvariety by proving that it has finite mass with respect to the background metric. If you can do that, then the current extends, and this implies Bishop's extension theorem. Bishop's extension theorem is proven in a different way, very different way. It's about the topological closure of some subvariety across a hypersurface. So you take the topological closure, and provided that the volume is finite, then you get the topological closure being complex analytic. Okay. And how does it relate to current extension theorem? So Skoda theorem is using the theory, of course, by definition using current, and it uses green kernels and so on. So everybody should have read, or if not, you should read this article. So then you have the extension theorem. And if I give you a subvariety, it supports what is called the integral current on the smooth part of the subvariety. And then you extend by means of Skoda theorem. And then you recover the extended analytic subvariety by making use of Seo's theorem. So this is a very neat way to prove Bishop's theorem using finiteness of the volume. Now, why is that all of this important for me? The title was starting with Gauss-Bonnet formula, and I wanted to prove rigidity theorem. First rigidity theorem I proved was the Hermitian metric rigidity. And then has implications for maps. And so in some sense, it recovers in the Hermitian symmetric case, rigidity results for maps into manifolds of non-positive curvature. So this type of results, you can prove it. But then these are not the only rigidity theorem. I want to look at others. The first thing I want to look at is a mixture between a negative curvature and flat curvature. So what is a Siegel modular variety? The Siegel modular variety is actually the variety whose base is the base is equal to the Hg mod gamma. So you take Hg mod gamma, and then already in the case of degree 1, you have of elliptic curves, you have singularities also. So there are some divisors in infinity, some subvariety at infinity. And then these are fibers which are the abelian varieties. You take gamma, which is slightly smaller, finding this subgroup in SPGZ, so that it has no fixed point, it's torsion-free thing. Then you can have this Kugel family. So this guy is a mixture of negative curvature and flat curvature, because the fibers are flat, and then the base is actually negative curvature. All right. So this leads me to the following study. There's something called the Mordell-Weil group. You can think about this as, okay, so let's say you take this
this guy, I would call this xg, and I would call this ag. So let me use this notation. This is not the same. I don't know what notation to use. It might be ag. This is easier to see. So over this xg. Okay. But this is a model of something which is an abelian variety, a polarized abelian variety over a function field. You may think of this as something like this, A, G, K, where K is the field of meromorphic functions on the closure of this xg. Okay, so this is a function field. So then you can study, therefore, the Mordell-Weil group, and this was studied. This was studied by Schroeder. Schroeder, I think, in the so Schroeder's theorem says the following: that if you take the case of elliptic curves, there are no sections of infinite order. So that was at the background of my study of this. So I look at this Cougar families. These are called Cougar families, and you look at their Mordell-Weil group as an abelian variety over a certain function field, and I want to prove the same statement. This was done already by the number theorist Silverman had the proof, which works for the xg and other cases. And then there were various works in that. And so let me just now provide again my philosophy. You don't just prove new theorems. You look at theorems that exist, might be viewed from different angles, and you try to give another proof which might be more flexible. And then perhaps you can go much further. So you are sort of reassured that you are not trying to prove something that is in fact false. You know it's true. So you have some confidence that there should be some other way of explaining it. So that's at least how I look at it psychologically. Right? So I'm sorry to bother you, but I don't. Yeah, can you tell? Okay, fine. That's the third one. Okay, good. Yeah. So I look at this problem and trying to prove that there is no section of infinite order. So how did Schroeder do it? Schroeder did it with the. Schroeder did it with the algebraic geometry. This is a surface in the case of elliptic curves. So you have this is a divisor, and this divisor then gives you an element of the Picard group. So he did this by studying the Picard group and looking at Chern classes and so on, and show that in the modular case, actually there's no contribution from horizontal divisors. So that was a proof. So how was it proven for the Ziegler modular variety of by Silverman and other cases? What she did, well, not Silverberg, of Silverberg, when this was in the 80s, also early 80s maybe. Then she looked at this. So Silverberg looked at this and tried to prove that that does not exist in infinite order section. So by some density theorem, you have copies which look like the elliptic situation. You can embed some curves inside, the diagonal curves and so on, into it, and there's some density theorem. So on each, you know that the group is torsion. So you estimate the torsion. If you have uniform order estimates on the size of the torsion, then you can conclude that this global section must be flat along these directions, and due to some density statement, you can prove that this section is actually by itself torsion. That is the approach. So this approach is to take the elliptic surface situation as the prototypical situation, and then do things by restriction. Now, I wanted to look at it from differential geometric point of view. From differential geometric point of view, you have rigidity for higher rank situation. You don't have rigidity for rank 1. So from the differential geometric point of view, rank 1 situation is most problematic. Higher rank situation should be more rigid. So this completely reversed the orientation of the research. So for instance, once you fix this approach, then you can do the following. I just look at the tangent bundle. So for instance, in this case, so take a point here, and then you decompose this. This projects to here, and this has a Hermitian metric. And therefore, by defining what is horizontal, then you would have a metric, not just one metric, a family of metrics. because you are allowed to scale the metric downstairs. So you can take, well, here you have the Euclidean metric, and here I will identify it with a curve here, and then I use the metric downstairs. And then I take the sum of them with the scaling. Okay, so then I will have a family of such Hermitian metrics, and then I can do the Gauss-Bonnet argument. So what is this metric? What I did was actually I just write down this metric by using the decomposition. And so what is the horizontal one? There's an obvious way to define a horizontal one. This is a certain real linear combination of the lattice. And then you define what are called horizontal sections. For instance, this could be a torsion section, but it could be, but if the coefficients are rational, you have a torsion section, right? So then, after you define this, I check that this is actually Kähler. The fact that Kähler comes from the, actions of the circle group. So you can see it easily. So this is Kähler metric. And so you have a family of Kähler metrics, and then I do the Gauss-Bonnet argument. So here is this. So the way to prove the vanishing is the following. Suppose I have a section. A section then is a map from here. So I can decompose the differential of the map. I can take this d sigma and decompose it. So the vertical part, so it's already written here. So d sigma projects to the vertical part. It's all right. Yeah. Okay, I know. Okay. So you have this d sigma. The vertical part of it will be given by this eta sigma here. It's done already. It's done. Okay. Yeah. So it's given by this eta sigma. So this eta sigma. So to prove that it is a torsion section, it suffices to prove that eta sigma is equal to 0. Okay. Now, so how does one do it? There are two different ways to do it. Okay. Now, so here, so this is the mu. Mu is the form which restricts to this horizontal sections are equal to 0. Okay. So if you look at this metric, so if I restrict to this, of course, I get a Kähler metric, but this is coming from the base. If I ignore the base, I still get a metric, semi-metric. The semi-metric measures in the Euclidean direction, and it's equal to 0 along here. I call this mu. And in recent years, this came back to be an object of intense research, actually, and this is called a Betti form. This is now called a Betti form. So I look at this Betti form mu, and then actually, this form first appeared in the work of Satake, except that he was looking at this as a means, as a component improving the embedding theorem on the Cougar family. So he looks at some Kähler metric, which is the curvature of some ample line bundle on the total space. And this is actually equal to what I did. Well, my perspective is to take this as a form which has a kernel. The kernel is precisely given by the flat sections. Okay. So now let me explain why all this is important. Okay. Now I want to prove. Let's say that. Let me try to reprove Silverberg's theorem. So what I did is this. I look at okay. Now, actually, I had two different proofs of Schrödinger theorem. So let me explain the proof. For Schrödinger theorem, it's the following. This came from some work that was done in 48 by Bo in a German, probably Mathematischen, or some German journal, so as far as I remember, where he proved that if you have a certain modular, a certain section, so take the upper half plane, and you have a certain section, and you have a group acting on it, gamma, SL2Z, or some finite index subgroups, and if if it transforms like that of a vector bundle, together with the addition of some admissible terms, like in the case of the lattices, some real linear combination of lattice, or actually integral combination of lattice. You take such a function which is defined in the upper plane, and you, in this particular case, when you take the second derivative, it is actually a modular form. This is quite surprising. You're taking a section like this. You take what is called an elliptic logarithm, so it becomes a map, a section of the upper half plane over here, and you take this guy, and then you take the second derivative. Only the second derivative and nothing else. It becomes a modular form. This is a sort of analytic way of defining a modular form from a section like this. Right? So then the holomorphicity of this form, of course, you take second derivative, of course, it's holomorphic. Now I have differential geometry, and the differential geometry comes from this matrix, and then you take this section sigma. Okay, so you have this. So this turns out this Napla is using the metric. Napla of eta sigma is holomorphic. And because Napla of eta sigma turns out to be exactly second derivative of f. Why should that be the case? It is very difficult to define two objects, the two sections of the same bundle canonically and sort of functorially that are well defined and invariant. Right? So I fathom that they must agree with each other, and that indeed is the case. So you look at this equation. So this equation, you look at this equation, and since I have differential geometry, I can do commutation. That's what you do in differential geometry. And then you get an eigensection equation with a negative eigenvalue. So you have negative eigenvalue, and such an object cannot exist provided that you can do integration by part. Right? So this Kodaira vanishing theorem is based on this type of argument. Now, there's a difficulty there on a non-compact object. So it's omega h mod gamma. So I have to justify this, and I would just be able to justify this provided that the form eta sigma is square integrable. That's what you do with finite volume case. So how do I do this? Well, I do this by proving that actually mu extends as a current. So this is a central theme in theory of currents. But how do you prove extension of current? This is a hypersurface, and you don't know about the mass and so on. What I did was I put this thing into the A2. So abelian surfaces. Then you have the Satake compactification, and this has codimension 2. Of course, this is singular. You also compactify the fiber bundle. It's singular. But even for singular things, you have an extension, and then you pull back a smooth version of it, and then you have finiteness of the mass. So this extension means that in a non-singular model of it, you have finite mass. And using that, you can conclude that actually when you restrict to the one-dimensional case, you still have finite mass, and you still have extension. Okay, so that gives me the extension, and then I can do integration by part. So this everything here relies on Schrödinger theorem. So, okay, so then I make use of this with Tho in an article in '93, where I prove not just the case of Siegel modular, but actually for any Cougar family, provided that you don't have any constant part. Of course, if you have a constant part, you could have section. Constant part means that the abelian variety split into product, and up to finite order, finite covering split into product, and you have a fixed part. So I assume that this is not the case. Then you can prove that there are no sections of infinite order, no element of Mordell-Weil group of infinite order. This problem was approached also by M. Saito using Hodge theory, but one needs classification, and only under certain assumptions on the Cougar family could one prove this using Hodge theory. So this is, in a way, for this particular problem, is more powerful than just using Hodge theory. The geometric origin, as I said, is that when I think about the Siegel modular variety, I saw immediately that you have the finite theorem, because it's more rigid. And when you do the Gauss integral, you look at the pullback. So you have this family of metrics. So I can scale, right? So this is a Kähler metric. And when you restrict this Kähler metric to here, and then there's a parameter t. So you have a family of metrics. For this family of metrics, you have the Gauss-Bonnet integral, the integral being equal to 0. But now this can be expanded in terms of t. And the first term that appears is actually the same as the integral for metric rigidity theorem. Therefore, I saw immediately, if you take this approach, the Ziegler modular case already is proven. Okay. Now, so how about the Schroeder theorem? As I said, I first proved it using the Gauss-Bonnet integral. The Gauss-Bonnet integral, you use this mu and restrict to this section and do the integration. Maybe you can do it plus the pullback of this metric so that it's indeed a metric. You prove this. And then you have to check the Gauss integral. Of course, in this case, you don't have flats. So the integral is some non-zero number. So you have to check two constants. So you have to check that the constants give you a contradiction. And this could be explained by the negativity of the eigenvalue when you apply to this Laplace, positive Laplace type operators, nabla bar star nabla bar. So you can look at this in this way. So if you look at it from the eigensection point of view, then you see it from the negativity. If you do it from a Gauss-Bonnet point of view, it's computing two integral and checking that they do not agree, the constants do not agree. So in this sense, the eigensection equation looks more transparent. So then this could be applied to the rank 1 case, and then we apply it in all cases using the uniform approach. By looking at some eigensection equation satisfied by such a section if it indeed existed. Okay. So this is explanation. I can take the metric, which is a sum of, so you take sigma pull back. This is an integral on the base. You take the section and you pull back this Betti form. And you have a parameter t there, and then you integrate. And then you expand in terms of t, and you get a contradiction. In the case of higher rank, immediately. In the case of rank 1, you have to do some computation. Okay, so this is explanation. Now, when you look at this, well, it's a general case, not a Ziegler modular case. You look at the universal bundle. The universal bundle over a Shimura variety of abelian type, actually you may have flats. You may have flats. And this differential geometry only applies to those components of the universal bundle which are not flat. So they are they have non-positive curvature and not identically equal to 0. For these, you can use the eigensection equation argument. When I first did this, at our time, we didn't have emails and all that. We sent preprints to people. And M. Saito kindly let me know that there are cases where you have flats. So it seems like this only proves the vanishing on certain components on the decomposition. But it turns out that by using very elementary algebraic number theory, you can prove that. As long as you can prove certain components are flat, are 0, the other components have to be 0 to be equal to 0. You want to look at the monogeometry, and you use only very elementary algebraic number theory, named by taking traces and so on. So differential geometry works for certain components, and the rest is taken care of by algebra or arithmetic. So this is also the philosophy I want to do. So complex geometry can enter into number theory by providing techniques that works with certain components of the problem. And then the rest you have to take care of by algebraic means. Okay, I want to point out one theorem, or one theorem and then one problem that I have posed and which has never been studied up to this point. So if you look at this and you look at the cross-section, allowing the logarithm to have real coefficients instead of integral coefficients, you can actually give the precise dimension of the set of solutions. These are not, you may call this a multi-valued sections, this multi-valued sections. You can compute this number, and this is exactly given by a number which is determined by the classifying map. You have a map from a base B into X gamma. And then you have the ramification of this map, and the size is precisely equal to the ramification. Okay. So then the question is the following. Well, you want to determine, since I can bound it by the size of ramification of the classifying map, you can ask how to determine the actual rank in terms of the positions of the ramification points. Now, then this is actually Hodge theory in some sense. It's Hodge theory because you are looking at classes obtained by these multivariate sections, and you're looking at the cohomology, H2, of the elliptic surface obtained, and see whether this comes from a rational point. If it comes from a rational point, then it can be given after multiplying by a positive integer as a section. So this is Hodge theory, except that this Hodge theory is now translated into a Hodge theoretical problem on the base curve instead of on the surface. So this should make the problem much more amenable to study. I think this is an interesting problem. So the question is to determine the rank in terms of the size, in terms of the ramification. I think if you study a special cases like from P1 to P1, you take a polynomial map and get infinities being mapped to infinities, then you raise the question how you determine the rank in terms of the ramification points. Yeah, and then this of course also gives me, by making use of this Betti form, later known as Betti form, one can define the pairing, and this is the height function, and this is what I already called the canonical height function, except that I didn't prove that it satisfies the usual axiom for height function. This can be done. I think Gautier has proven this in the context of dynamical systems, but in the case of abelian varieties, you can prove it by easier methods by making use of the complexifications. Okay, so now let me move on to other things. So I want to say that the Betti form has been proven to be very useful. It was developed used by Zanier and Cauvage and Messer and another collaborator. They were working on this. André was involved, I think. Then there was the work of Gauss later on, where he studied an extension of my theorem with Jacob Zimmermann and Jonathan Piller, proving the action well. This is another topic, so I'm not talking about that. But Gauss proved this for the mixed situations, or mixed Shimura varieties of abelian type first. And then he made important use of the Betti form to do that. And this element was used in the first proof of the uniform Mordell the theorem for the curves embedded in or mapped inside their Jacobians. So the Betti form turned out to be very important in recent research in number theory. Also, I think Yuan Xinyi and Xie Junyi, they were also working on this. Well, they do some geometric Bombieri length theorem by making use of some partial height based on the integral over some open set. Okay. So I will run over this just to say that this was work done already by myself, and with To was done in the 90s. But after the Betti map became popular, there were important questions raised, and we also tried to make use of general geometry to deal with them. One is to estimate the Betti multiplicity, and this can be done by an analog of the Poincare-Lalonde equation. So if you use a differential geometry and you take the vertical part of a section, then actually they satisfy some differential equation, first order differential equation, and then a second order differential equation. So my work with To was with the second order. And then we proved something like this. This was first done by Zanier collaborators by an ineffective method using old minimal theory, and then done by Uzua and Ulma by using the winding number. And then I did this with Sui Chong by making use of this differential equation. And let's see, am I going, yeah. I should go back this way, yeah, sorry. So this was a theorem I proved with Ng. So the Betti multiplicity is actually the vanishing order of eta sigma. And then you can count the vanishing orders, and the sum of the vanishing orders actually gives you a formula. And this is a formula, the vanishing order. So this work published in 2023. Okay. And this is the first order differential equation. Now comes to another thing which involves the rigidity theorem. This is the question of commutants of Hecker correspondences. And to cut things short, Clozel-Ullmo posed this question, and I was visiting Oxford, and then I got interested in the problem. They were trying to ask when T is a correspondence defined by a Hecker or correspondence, which is in some sense non-trivial, an exterior modular correspondence. They were looking at the commutants. So this is another thing I want the new members of our community to know. So one should keep track of what is being done and questions being raised in other fields of mathematics. And one great thing they did was to translate the problem into two problems in differential geometry. And then I solved this. So I solved one of the problems with Sui Chung about measure preserving maps, because they were looking at these commutants, and this S then becomes something in the product. And when you come look at it from the base over a generic open set, actually it's a multi-value is a function in the product of omega in the omega product of omega. And then they translate the problem into two different problems under different assumptions. One is into measure preserving map, and the other is into holomorphic isometries. So in order to do the measure preserving map, what I did was to make use of works of Webster and Huang in CR geometry. So CR geometry will allow one to prove this. There were many steps in the proof, but let me just skip it. It's essentially CR geometry. Interpretation of the pseudo of the Levy form in terms of the curvature. So when you have a measure preserving map, it maps a unit sphere into unit sphere, and therefore you can translate this into questions of CR geometry. The unit spheres are algebraic because they are defined explicitly. And then there was another question. The other question is in the case of the holomorphic isometries. And this I did in an article in 2012 on the isometry, and with characterizing a holomorphic isometry from omega to omega prime. But I relaxed the condition by just allowing omega and omega prime to be bounded domains, and then that they are defined by certain functions. And then I need the requirement that the Berman kernel be rational in ZW bar. So that's all. And I did this. The basic thing is to make, first of all, to make use of the functional identities and coming from Calabi, and this was what Clozel-Ullmo did. But the difficult part is how to extend it beyond the boundary. So I did this. And then I found an example of holomorphic isometry of a higher dimensional ball in the biosymmetrical domain. For some time, I did not know if they exist. And I found this example by working with the VMRTs. So you take a point, you take on the boundary, the regular part of boundary, and you take the union of rational, minimal rational curve or projective lines passing through it, take the union and take the intersection with omega. Then I prove that this has holomorphic sectional curvature equal to -2 under normalization, and therefore is the image of a ball. And this turns out to be very important in later work. So maybe I just say something. This is the gamma, yeah. So Finsler-Bentrich rigidity theorem. The Finsler rigidity has to do with not looking at Hermitian metrics, but just looking at a Finsler matrix defined. And then I only restrict to the VMRTs, and then I prove their rigidity. And this turns out to be, well, this was something I did a long time ago. It was, for instance, an article in 2004. But this turns out to be important in the study of the spectral base. And in a very recent article, okay. So here, in this last article, I had worked with He and Liu, He-Liu and He Xiji, where we proved that the spectral base, this has to do with moduli spaces of Higgs bundles and so on, that they vanish in the case of omega mod gamma. I want to just make the statement about one theorem. with work I did with Wong. Well, of course, I was looking at metric rigidity theorem, so omega mod gamma into omega prime mod gamma prime, or something Kähler metric with non-positive curvature. But then I can also ask the following question: can I relax condition on the curvature? To require non-positive curvature is a lot of requirement. There are few examples beyond the symmetric. There are certain homogeneous domains you can do that. But if I require Finster negativity, this is true for any bounded domain. So I want to prove something like from omega mod gamma into d mod gamma prime, which d is a bounded domain. I only make use of the Kähler-Theodori metric. And then I want to prove something which is a rigidity. And it turns out to be possible. It relies on, at the beginning, with the Finster metric rigidity, but eventually with methods of harmonic analysis and also ergodic theory. And let me just say that in the study, what we have to do is to look at the pullback of bounded holomorphic functions, because I have bounded holomorphic functions there. I pull them back, and then I study this space. And it turns out that this can be done by using Moore ergodicity theorem and using the boundary values on the ball. The boundary values on the ball, where are the balls? As I said, this example of embedded ball, this turns out actually to be the fiber of a Kähler projection. So I look at Kähler projection and then study that. And that gives me this theorem. So let me stop here. Thank you.